Hello class, today we're going to do rational numbers and decimal representation, section 6.3. Okay. Alright, so we're going to define and identify rational numbers, write a rational number in lowest terms, add, subtract, multiply, and divide rational numbers in fraction form, solve carpentry problems using operations with fractions, apply the density property and find the arithmetic mean, convert a rational number into a fraction form to a decimal number, convert a terminating or repeating decimal to a rational number in fractional form. Alright, so let's start with the definition of rational numbers. So we've seen this before, but let's review it again. X, such that x is a quotient of two integers with a denominator not equal to 0. A rational number is said to be in lowest terms if the greatest common factor of the numerator, which is the top number, and the denominator, which is the bottom number, is 1. The rational numbers are written in lowest terms by using the fundamental property of rational numbers. Now, the fundamental property of rational numbers states that if a, b, and k are integers with b not equal to 0 and k not equal to 0, then a times k over b times k is the same thing as a over b. Essentially what happens here are these cancel themselves out. Alright, let's write 24 over 27 in what we call lowest terms. Okay. Now, in order to do this, we need to break down 24 and 27 into different terms. Okay. So, ideally into two terms that have a common term with each other. So here you can see we chose to break down 24 into 8 times 3. We chose to break down 27 into 9 times 3. The reason we did that is because the 3's will cancel and it'll leave this in the lowest term of 8 over 9. Okay, so that's why you really have to know your multiplication facts. All right, for rational numbers a over b and c over d, with b not equal to 0 and d not equal to 0, because you don't want your denominators to be 0. A over b equals c over d if and only if a times d equals b times c. Okay, A and D are called the extremes, and B and C are called the means. Okay, so if A over B and C over D are rational numbers, then A over B plus C over D equals A times D plus B times C over B times D. Okay, and if we're looking at a subtraction case here, A over B minus C over D equals A times D minus B times C all over B times D. Essentially what we're doing here is we're working with fractions. And in order to work with fractions and add and subtract them, we need what's called a common denominator. That's all we're essentially doing here. Okay, so for this first one with this addition, we want a common denominator of B and D. The easiest way to do that is just to multiply the two on the bottom. So your common denominator here would be b times d. Now note that if you did that, what you essentially did with the first fraction was multiply the entire first fraction by d over d. And then what you did with the second fraction to get the b in it is multiply the entire fraction by b over b. Now, we both know that d over d is the same thing as 1 and b over b is the same thing as 1. We can multiply anything by 1 and get the same thing. That's why we're allowed to do this here. So what we get is that a and d, that c and b, or b and c here, and that d and b. The same thing's done with the subtraction. Okay. In practical problems involving addition and subtraction of rational numbers, fractionals are usually rewritten with the least common multiple of their denominators called the least common denominator. Okay, so let's perform each operation here. We have 4 over 9 plus 2 over 15. Okay, now for the first one here, what we're going to want to do is we are going to want to get a common denominator here. Okay. Ideally the least common denominator. Okay. Now you can already see because I clicked over to it, the least common denominator here is 45. All right. Now that's not 9 times 15. You could go that route just like the definition did before, but ideally using the least common denominator lets you use the smallest numbers possible to get to the quickest answer. Okay. Now the reason we use 45 is both 9 and 15 will multiply to be 45 by some other number. Now, what number does it take to get 9 to be 45? Well, that takes the number 5. Okay. So essentially what I'm doing is multiplying this first fraction by 5 over 5. 5 times 9 is 45. 5 times 4 is 20. That's where this 20 on the top came from. Now for this 15, we also want it to be 45 so that the denominator is the same. What did we do to make that happen? Well, we multiplied 15 times 3. So we also need to multiply 2 times 3. That gives us the 6. Now 20 plus 6 is going to give us 26. And that's going to be over 45. And we're able to do that because we have that common denominator. And I obviously clicked over to it as well. Now let's try this one. Here we're doing a subtraction. Same numbers, just a subtraction. We've got 4 over 9 minus 2 over 15. We can use this same common denominator here. We can use the 45, okay? And we'll do the same thing essentially. Okay, we'll multiply the first fraction by 5 over 5 and the second fraction by 3 over 3. Oops. To get 20 over 45 minus 6 over 45. Now 20 minus 6 is 14. You don't subtract the denominators though, you just keep the same denominator there. So it's 14 over 45. Now let's look at a multiplication case. Okay, if a over b and c over d are rational numbers, then a over b times c over d equals a times c over b times d. Okay, essentially all you're doing is multiplying across the top and multiplying across the bottom. So let's try to find the product here of 5/9 times 3/10. All we've got to do is multiply across the top and multiply across the bottom. That just means we're doing 5 times 3. That's 15. And then we're doing 9 times 10. That's 90. Okay. Now, the one thing we are going to want to do here is put it in simplest terms. Okay, because 15 and 90 actually have something in common. Something that will go into both. Well, what will go into both? 15 actually. So there's a couple ways to do this. You can break it down like the solution did here, or you can just divide both by 15. Okay, if we divide both by 15, 15 divided by 15 is 1, 90 divided by 15 is 6. So that reduces it to 1/6. If you would rather break it down into its multiples here, like it does in the solution, we'd have 1 times 15 over 6 times 15. We would notice that the 15s cancel out and we're left with 1/6. The good thing here, like I said, especially in the entry level classes, a lot of times you're able to use a calculator, and the calculators a lot of times, especially the TIs, will just go ahead and reduce these for you. If a and b are real numbers with b not equal to 0, then a over b is the same thing as a times 1 over b. Okay, and if a over b and c over d are rational numbers, then c over d is not equal to 0, then a over b divided by c over d is equal to a over b times d over c, which equals AD over BC. Okay, now this is what I call, and what you've probably heard of as the keep, change, flip scenario. Okay, so if we're dividing fractions, we're going to keep the first fraction. We're going to change the sign from divide to multiply, and then we're going to flip the second fraction. That's all that's been done here. Then you can just multiply across the top. A times D is AD. B times C is BC, and we're done. Let's look at an example. It says find the quotient 2/9 divided by 5/6. I'm going to keep the first one, 2/9. I'm going to change the sign, and I'm going to flip the second one. Okay, that's all we've done here. Then all we have to do is multiply across the top. 2 times 6 is 12, and then 9 times 5 is 45. So I have 12 over 45. Now we do have to reduce that. Okay, so you can break it into its common terms here. You can break 12 into 4 times 3 and 45 into 15 times 3 here. That'll allow the 3's to cancel, and you can be left with 4 over 15. What I'm going to do for you, if you're up for it, I'm going to show you a little secret here. And if you can follow it, follow it. If you can't, it's okay. This one's a little advanced. What I like to do when I have it right here, in this multiplication terms here, I like to look at it a little more simple. I like to look and say, well, can 2 be simplified into 9 or 5? No, it can't. Can 6 be simplified into 9 or 5 though? Yes, 6 can. 6 and 9 have a common factor of 3. So I could technically just cancel a 3 out of both of them. If I were to cancel a 3 out of both of them, then essentially what would happen is 6 divided by 3 would become a 2, and 9 divided by 3 would become a 3. Okay. Now, you might even want to see it as this is the same thing as 2 times 3, and this is the same thing as 3 times 3, which means that one of these 3's will cancel. And that means I'm left with 2 times 2 instead, which is a 4. And I'm left with 3 times 5 instead, which is a 15. And I'm already to reduced form without even having to go through the 12 by 45 step. Now, if you don't get that, it's okay. It's okay to go to the 12 by 45 step. It's even okay to use your calculator to help you a little bit here. All right, let's look at a practical example. It says a carpenter has a board 72 inches long that he must cut into 10 pieces of equal length. This will require 9 cuts. Okay? If each cut causes the waste of 3/16 of an inch, how many inches of actual board will remain after the cuts? And what will the length of each of the resulting pieces be? This is a technical problem. All right, we start with 72 inches and we must subtract 3/16 9 times for 9 of the cuts that are going to happen on this board, because the board starts 72 inches long, but every time we make a cut, we're going to waste 3/16 of an inch. So our first setup here is going to be 72 minus 9 times 3/16. Okay? So what I'm going to do is represent this as 2 multiplied fractions here. I'm going to change that 9 into a 9 over 1, and then essentially all we're doing here is multiplying. Okay? That's going to give us 9 times 3, which is 27 over 16. We're going to subtract that from 72. Now, in order to do that, I need to set that up. You can, if you want to do it on the calculator, you can. But if you were to do it by hand, we would have to set this up here as 72 over 1 minus 27 over 16. And then we would have to find a common denominator here. That would be a 16. Okay? I'm going to leave the 27 over 16 alone because it already has that denominator. But now I've got to change that 72 into a numerator that would be multiplied by 16. So essentially what I'm doing here is changing the denominator. In order to do that, I'm multiplying by 16. 16 times 1 is 16. 16 times 72. That's going to give me 1,152. And then I can subtract the 1,152 from 27. That is where I get the 1,125 that's in the numerator for my final answer there. But remember, this is not the end of the problem here. And I can even convert this to be this mixed number here of 70 and 5/16. Okay? That's how much of the board I have left after it's all cut up in total length. But also remember, there's another step to this problem, because now we want to split that remaining length into 10 pieces. Okay? So in order for it to be divided into 10 pieces of equal length, what I need to do is divide it by 10. So if I keep the fractionoid part of it here, I've got 1,125 divided by 16 divided by 10. And remember, what I need to do here is I need to keep the first one, change the sign, and flip the second one. Now, technically 10 is the same thing as 10 over 1. So if I were to flip it, it would be 1 over 10. Okay? So I'm essentially now just looking at 1,125 over 160 if I were to multiply it out. Okay? Now, I need to reduce that. And when I do reduce that, okay, I reduce it down to 225 over 32. Now, if you want to go through that reduction step, essentially what I'm canceling out of each is a 5. Okay? Because 160 divided by 5 would be the 32, and 125 or 1,125 divided by 5 would be the 225. That will bring us to that simplest form. So each one of those have equal length. If I put it in mixed number form of 7 and 1/32. So each of those 10 lengths are 7 and 1/32 inches long. Okay, easy enough. Now, let's look at the density property of rational numbers. If R and T are distinct rational numbers with R less than T, then there exists a rational number S between those two rational numbers. This leads to the conclusion that there are infinitely many rational numbers between two distinct rational numbers. Essentially, if you have two distinct rational numbers, you can always find another rational number that are between them. And what that means is if I can always find something between the other two, and there's always something between those two, there are infinitely many somethings out there. Okay, in this case, rational numbers. Now let's look at what we call the arithmetic mean. That's what it leads us to. To find the arithmetic mean, or the average of n numbers, we add the numbers and divide by the sum of n. For the two numbers, the number that lies halfway between them is their average. Okay, so if I wanted to find the average of 3/5 and 2/3, I would just need to add them together and divide by 2. Okay, so that's essentially what we're starting with here. We're adding together 3/5 and 2/3. Now remember, in order to add these fractions, I'm going to need a common denominator. Okay, the common denominator of 5 and 3 here, the least common denominator is 15, which is just 5 times 3, which means I need to multiply this first one times 3 over 3, and I'm multiplying the second one times 5 over 5. Now 3 times 3 is 9. 2 times 5 is 10. So now I have 9/15 plus 10/15, which gives me 19/15. But that is not the solution to this problem, because we're trying to find the average, which means I need to divide that whole thing there by 2. So 19 over 15 divided by 2. I keep the first fraction, I change the sign to multiply, and then I flip the second one. Remember, 2, same thing as 2 over 1. If it's flipped, it would be 1/2. So now I'm looking at 19 times 1 is 19, and 15 times 2 is 30. So, what's halfway between 3/5 and 2/3? 19/30. There you go. That is the solution to this problem. That is the arithmetic mean, or what we call the average of those two numbers. So I can either divide by 2 or multiply by 1/2 to find the arithmetic mean of two numbers. Remember, if you're doing 3 numbers, you'd have to divide by 3. If you're doing 12 numbers, you'd have to divide by 12. Now, let's convert a rational number in fraction form to a decimal number. A rational number in the form a over b could be expressed as a decimal most easily by entering it into a calculator, which we have the ability to do. We have TI-84. It does a great job on it. You can always go back and review those lectures where I show you some of the calculator secrets to help you do this. For example, to write 7/8 as a decimal, we're going to enter 7 and enter the operation of division, enter 8, and then press equals, find the key, find the following equivalents. Okay, that would be on the calculator. Obviously, if you wanted to do it otherwise, you would have to come over here and you would have to try to divide 8 into 7. You know that there's a 0 there. You have to add a 0 here. 8 goes into 70 8 times. 8 times 8 is 64. Lord have mercy, we're subtracting now. I have 6 left over. I'm going to bring down an additional 0. 8 goes into 67 times. 8 times 7 is 56. That leaves us with a 4. I have to add another 0. 8 goes into 45 times. 40 minus 40 is 0. So I could do it by hand, but the calculator would definitely make this easier. Any rational number can be expressed as either a terminating decimal, which means it stops, or a repeating, which means a recurring blocks of numbers decimal. Okay? A rational number in lowest terms results in a terminating decimal if and only if prime factor of the denominator is a 2 or a 5 or both. A rational number in lowest terms results in a repeating decimal if a prime other than 2 or 5 appears in the prime factorization of the denominator. Without dividing, determine whether the decimal form of the given rational number terminates or repeats. So for the first one, it's going to repeat because there is a factor of 3 in the denominator. Okay, and 3 is a prime number, right? Because here, let's go back to repeating decimal definition. A rational number in lowest terms results in a repeating decimal if a prime other than 2 or 5 appears in the prime factorization of the denominator. Now the prime factorization of this denominator is 3 and 5. So here we have a prime other than 2 or 5 that is available in this denominator. That other prime is 3. Okay, so because there's a factor of 3 in the denominator, it repeats. Now, if we look at this one and we broke it down into its prime factorization, we have a 4 and a 4 here, which breaks down into a 2 and a 2. And this one also breaks down to a 2 and a 2. So its prime factorization is 2 to the 4th. So it terminates because it only has a 2 or a 5 as its primes in its denominator. Okay? Write each decimal as the quotient of integers. Okay? Now, if I had to convert a decimal into an integer here, or a quotient of integers, I just have to remember what place I'm in. Tens, hundreds, thousands. I'm in the thousandths place here. So what I'm going to do is take this number, the 759, and put it over 1,000. That is my solution. Now here, I'm in the tens place. Okay, so what I need to do is put the 78. You can do it two ways. You could put the 78 over 10 if you want to, or you can write it as 7 plus 8 in the tens place. Either way, just depends on if you want to write it as a mixed number or if you want to write it as a total fraction there. But do keep in mind that if you do, or when you do write it as 78 over 10, you're going to want to put that in lowest terms. Okay? We have a common number here. 2 will go into both of these. So in order to reduce 78 over 10, I need to take 2 out of both of them. If I take 2 out of 10, it leaves me with a 5. If I take 2 out of 78, it leaves me with a 39. And I have it in reduced fraction form now. Now, this completes this chapter. If you have any questions, send me an email and let me know. Other than that, I will see y'all during the next lecture.